This lecture is from Unit 6 of the AP Physics 1 curriculum. This is the second part about torque and work. So imagine you're trying to open a jar lid. If you take your hand and twist, then you might be able to open that lid. This application of a force, which is attempting to rotate an object about an axis, is called torque. In a sense, torque is the rotational correspondent of linear force. It causes a change in motion, but in a circular direction. Just as a linear force is a push or a pull applied to a body, a torque can be thought of as a twist applied to an object with respect to a chosen axis. For example, if you use a screwdriver, you can turn a screw by applying a torque. Now imagine you had to set up something like shown here, where you have a rod attached to a pivot point of some sort, and you've got a couple of masses suspended from it. And mass 1 is obviously larger than mass 2. But imagine in this situation that these two forces are balancing each other. The lever arm, the distance from where the force is applied perpendicular to the pivot point of mass 1, multiplied by gravity, would give us the weight of that. So we have R1, that's our lever arm, times mass times gravity, mass 1 times gravity, which is a force. And that's going to equal, on the other side, if they're balanced, the lever arm 2 times mass times gravity on that side. Now, if you only had one mass hanging on this rod, it would be spinning. It would tilt down, right? But if they're not tilting down, then that applies their twist must be related to the force that's being applied perpendicular and to the distance being applied, and that these two must be equal to each other. So the product of lever arm and the force applied at a right angle is called torque. If either the lever arm or the applied force increases, the torque increases correspondingly. Or if one goes down, the other goes down. So lever arm and force are needed, but it also has to be perpendicular. So really, the applied force doesn't have to come at a right angle. Only the perpendicular component would cause rotation in that situation. So the magnitude of the torque applied to a rigid body depends on three things: the applied force, the lever arm vector connecting the point about which the torque is being measured, and the angle between the force and the lever arm vectors. So in symbols, we could say the torque vector is equal to the lever arm vector times the force vector. That corresponds to the magnitude of the torque that we're talking about is equal to the lever arm distance times the perpendicular force that's being applied. If it's not applied perfectly perpendicular, then we need the perpendicular component, and we define that from F sine theta. The SI unit for these, for torques, would be a Newton meter. Now, quite often when we're talking about energy, we change the Newton meter to a joule. But when we're talking about torque, we don't do that. We leave it as a Newton meter. So here's a scenario. Suppose you're trying to open this door. So here's the hinges, here's the handle. But instead of pushing perpendicular, we're pushing at a 55-degree angle with respect to the door. What's the torque? Well, we only need that perpendicular component. Now, the actual application of the force is here. So the actual force vector is here. But we can figure it out as a component of a right triangle over here. In other words, we're going to take this diagonal and change it into an X direction and a Y direction. And we want the Y direction, that's the component of this force. So that would be the sine, since this is the opposite. So we want this side of this imaginary right triangle, and that's the opposite of 55. So that's sine 55 times the diagonal. So torque is the lever arm times the perpendicular component. In this case, that's 1.5 meters times the full force, 330 newtons, and then reducing that to find just the component in the perpendicular direction by multiplying by the sine of 55 degrees. And the torque in this case would be 410 Newton meters. If you have more than one torque applied to an object at the same time, then you have to add them together to get the total torque. And torque is a vector quantity, and so you're going to have to pay attention to which way the force is being applied. For example, here, what this is trying to show is it's pivoting here. So it's an irregularly shaped object, and it's not spinning in the center. It's kind of over on the side. This looks like it's coming up in the z-axis, but actually it's trying to show you it's spinning it toward the counterclockwise direction. This, on the other hand, is trying to spin it in the clockwise direction. So F1 is counterclockwise, F2 is clockwise. Those two are going to oppose each other. And so we're going to have to designate one of them as being positive and one as being negative. The convention is that counterclockwise is positive. Because if you imagine that this is your zero angle, the angle increases as you go counterclockwise. And so counterclockwise is positive. This is going to be negative. And so the sum of the torques, T1 plus T2, or tau1 plus tau2, is their lever arm times the force being applied. And we're assuming this is perpendicular here. That looks like a right angle. But we're going to use the force 2 and call that, well, that would be negative, and force 1 would be positive. And so maybe I've got those two backwards there. But the point is that we're going to designate one of them as negative, and we're going to have to do a subtraction rather than an addition. Now imagine you're trying to unscrew that jar lid, but it's not turning. Well, this is the application of two torques. You're trying to turn it one way, but something is holding it and applying a force in the opposite direction, that force being friction. If the lid doesn't move, we say that's in rotational equilibrium. The net torque, tau1 plus tau2, equals 0. If the jar lid is not only not turning, but you're not moving the jar at all, then doesn't have any translational motion, then it's actually in static equilibrium. That means the sum of all the forces equals 0. So imagine this setup here. We've got a thin wire or rod attached to the ceiling here, and then another rod or wire attached perpendicular to that, in which there's two objects that are suspended. So if the two metal orbs are attached by a very lightweight rigid wire suspended from a rigid point overhead, and the system does not move, calculate this distance from the suspension line to the center of gravity on the right sphere. In other words, how far is this point where it's actually being suspended to the center of mass of this object here, the right sphere? We have that the total distance from center of mass to center of mass. No, that's not the total distance. That's only, I'm sorry, we only have this side. So we've got 45 centimeters over here. All right. So the center of gravity, or center of mass of an object, is a point located at the center of an object's weight distribution. If the object is very symmetrical, then the center of mass is at its geometric center. But if it's irregularly shaped, the center of mass is closer to the heavier end. such as in the picture shown, the objects are, if they're not made of the same material throughout, if it's not a uniformly distributed mass, then the center of gravity might be very far from the geometric center. If we draw a free body diagram of our setup, we'd actually put a dot here rather than the entire sphere. But the point is that this has a weight that's pointed down, this has a weight that's pointed down, and we have a force tension on this wire or rod here. And those must be balanced. This plus this, the weights downward, must equal the upward force. We know that because it's not moving anywhere. It's in static equilibrium in the vertical direction. But what we're being asked to find is the point of suspension, and that doesn't really help us. For that, we need to look at the sum of the torques. If the sum of the torques equals 0, in other words, if these are balanced right here, then that means torque 1 must equal torque 2. So torque 2 is going to turn, if we had it all by itself, it would turn it counterclockwise. So we're going to designate this one as being negative. This one would turn it counterclockwise. This one's positive. This one turn it clockwise. This is negative. So that'll help us out. So the sum of the torques is mass times gravity times radius 1 minus mass times gravity times radius 2. So those two must be equal to each other if they add up to 0. If you do a little math, what we're trying to find is this value right here. What is the distance from this point to the center of mass of this sphere? So algebra shows us that it's M1 G R1 divided by M2 G. The G's are going to cancel, and then after that, it's just plug and chug. So it's 1 kilogram times 0.45 meters divided by 4 kilograms, and that makes R2 0.11 meters. So the distance from here to the center of the sphere is 11 centimeters. The whole point of applying a torque is to transfer energy, trying to put energy into or take it out of some system or object. All right. This movement of energy means that we're doing work. If this were a linear case, work means force times the linear distance. Well, we're going in a rotational sense. So for us, work done by torque is going to be the torque times the change in the angular position. Back when we were learning about the dynamics of objects that are moving linearly, we learned that generally what we're looking at is that work is any change in kinetic energy. So previously, that kinetic energy would have been translational. We might designate it as K sub T. Now we're looking at it rotationally, so we're going to designate it K sub R. So work done in a rotational sense is going to equal the change in rotational kinetic energy. Also keep in mind that work is calculated as the product of a net force times the linear distance over which the object has moved. Now that's in a linear sense, but we have the rotational equivalent. So if it's rotating, we want the torque times the change in angular position. Or I guess you would call that angular displacement if we want to use the correct terminology. So what this formula shows me is that if the torque goes up, the amount of work done goes up. If the angular position increases, then the amount of work goes up. So the work is directly dependent on both of these two variables. Now, I do want to keep reminding you that we're talking about rigid systems. In other words, the distance from where the force is being applied or the torque is being applied to the center of axis rotation, that's constant. It's not a flexible object that might have a changing radius. Here's an example problem. A 12 Newton meter torque applied to a flywheel rotates about a fixed axis with a moment of inertia of 30 kilogram meters squared. If the flywheel is initially at rest, what is its angular velocity after it has turned through 8 revolutions? So our formula is work equals tau delta theta. Torque is given to us as 12 Newton meters. The change in angular position is given us as 8 revolutions. But what we need is radians. And so we're going to have to do a little conversion here. So in 1 revolution, there are 2 pi radians. So 8 times 2 pi means that this delta theta is actually 50.24 rads. Now, although this is a perfectly good formula for work, that's not what we're being asked for, okay? It's asking us what the angular velocity is. And so we're going to need some more substitution here. We're going to need another formula, a little bit of a cat out of a bag here, and go back and remind you that we actually have another equation for work in a rotational sense. It is the change in kinetic energy in the rotation. And a change in rotational energy, kinetically, would be the moment of inertia times the angular velocity squared. So if we take the final angular velocity, subtract the initial angular velocity, this would be our equation for delta K in a rotational sense. But this, Wi, omega, excuse me, is 0. And so what we can say here is work equals 1/2 moment of inertia times the final angular velocity squared. And so if we take this and set it equal to our tau delta theta, our original formula that we are using, and then isolate this omega, now I think we're going to get somewhere. So now we have omega equals the square root of 2 tau delta theta over I, moment of inertia. And we've got all of those values. So the torque is 12 newtons. The change in angle was 50 rads. And the moment of inertia was given to us as 30. So just do the math, take the square root, and you get 6.34 rads per second. Also note that one of the things they like to do in AP is give you graphs of data if you had a torque versus angular displacement graph. Like how much is the angle changing as you apply, in this case, a constant torque? What would be the work done? Well, it's actually the area under the curve. The product of these two gives you work, torque times delta theta. So if it's a triangle, that would be 1/2 the base times the height. If it's a rectangle, it's the length times the width. It's the combination of those two things and take them apart and add them together and so forth. But the area under the curve. So remember, a lot of times in graphs, we want the slope, but sometimes we want the area. In this case, work done by a rotating object equals torque times angular displacement. Here's another example problem. A horizontally mounted wheel with a rotational inertia spins about a frictionless axle. At the initial time of 0, the angular speed is omega. A constant torque is applied to the wheel and causes it to come to a rest in time t. Derive an expression for the average power required to dissipate the wheel's energy in terms of I, omega, and t time. Now, power is work done per unit time. So what we're doing here is we've got say a disc spinning, and we're going to apply a torque to the outer side and use it as a brake and bring this thing to a stop. So its initial speed, omega 0, is some value. After a certain amount of time, the final time being designated with t, then the angular velocity is going to be 0. So this is going to be a little bit backwards from our normal use. The final is going to be 0, and the initial is going to be some value. So the torque being applied to the wheel is constant, and therefore the angular acceleration, how much this is slowing down every second, is going to be a constant. Just keep that in mind in case it's useful. So we're being asked to find the formula for power using only these three variables. Power is work divided by time, but this is what we use when we're using linear, so we're going to need the rotational equivalent of that. Well, work could be substituted with tau delta theta. Let's try that. And we'll give this equation. Now, we see t, and so we've got one of the right variables, but we have wrong variables here. So what we need to do is pull other equations off of the AP equation sheet or out of our heads. So we don't know tau, for example, but tau is the rotational equivalent of Newton's second law. Okay, so tau is the moment of inertia times the angular acceleration. So maybe that'll help. So let's put this in for our tau. So we'll take this little Greek t and we'll make it I alpha. Now, I is something we want, but we don't want alpha. We want omega. And so we're going to have to keep going here. So the angular acceleration is related to angular velocity. Again, go back to your AP equation sheet and look for an equation that has both of those in it. So here's a good one. We know this value is some initial angular velocity, and this is going to be 0, the final. And so we could find alpha from this. That seems reasonable. So alpha would be these two subtracted, divided by time. But remember, this is 0. And so we just need one of those omegas. I'm going to designate it as omega here because it told us in the problem that the initial angular velocity is omega. So here, this value and this value actually correspond. I know that symbology is going to throw us off a little bit, and I'm sorry about that. But this is actually some speed, and that's this right here. This is not the final speed. This is the initial speed. But anyway, if we put that in for alpha into our equation up here, we now have I, omega, delta, theta, negative, divided by time squared, because this was divided by time and this is divided by time. And I know this says delta t, but it told us that delta t equals the initial time was 0, and so the final time was t, so delta t is t. All right, so t divided by t times t on the bottom is going to give us t squared. All right, so now we have a good formula, right? Except that it's got theta in it, so we don't want theta, so we're going to have to keep going. So in an earlier slide, I had this equation on there, and I eventually derived this formula. So I'm not going to repeat that right now, but you can go back and review that. So if we substitute this, now we have just omegas in it, and so that's going to help us out a lot. So remember that this is a value that we're calling omega, and this is actually 0. All right, so we're going to put this as 1/2 omega times time, which is omega over 2t, and substitute that in for this delta theta right there. So here we do the substitution. Here was the original. Here we put w over 2t, or omega over 2t, excuse me. And again, this gets complicated mathematically. We have a denominator and we have another denominator, but basically one of these things is going to cancel out. This is going to square. And so now we have a formula. Power is negative moment of inertia times angular velocity squared divided by 2 times time. And that pretty much fits the bill. This has only the three variables that we were asked to find or to use. Technically, this is an average power because this time has some value. It's not instantaneous. So really, we probably should have designated that as power average. Now, again, we learned in this previous lesson that rotational kinetic energy is 1/2 the moment of inertia times the angular velocity squared. So if work is delta k, and if the initial well, we don't have to have the initial. I'm just going to keep the delta here. Is equal to 1/2 moment of inertia, angular velocity squared, change in. So there's going to be a final value here and an initial value. I'm going to take this 1/2 outside and this I outside the delta, because those things are not going to change during our rotation. And so we can have this as our equation for work. So that's perfectly usable. Remember, we could also have this equation for work, tau delta theta. And so we can substitute that over here if we want to and get this big, long, complicated looking formula, but that might help us out at some point. So let's look at another example problem. 55 Newton force is applied to the edge of a 5 kilogram disc with a radius of 0.35 meters for 4 seconds. The disc has an initial angular velocity of 6.5 rads per second counterclockwise. So it's going to be positive. Find the work done by the force and the angular displacement of the disk. You're being asked to find two things, work and angular displacement. Here's what we know. 55 Newton force, 5 kilogram mass, 0.35 meter radius, 4 seconds of change in time, and an initial angular velocity of 6.5 rads per second. You're going to be asked to find the work and to find the angular displacement. So that's delta theta. So here was one of the formulas I just derived a minute ago. If you want to use this formula, we're going to need this moment of inertia. Now in this case, we'd actually have to look that up. It's going to be 1/2 mr squared. On the AP test, they would give this to you, but we're going to have to look that up, and that's what it is on your sheet. So let's substitute that in, and we get 1/2 times 5, that's the mass, times 0.35, that's the radius. Don't forget to square that. So the moment of inertia is 0.3 kilogram meter squared. So now we know this value right here. We know the initial angular velocity because that was given to us in the problem. We don't know the final. When that happens, it's always a good idea to fall back on Newton's second law. In rotation, that looks like this, the sum of all the torques. In other words, the net torque, which is equivalent to net force, is the moment of inertia, which is equivalent to mass, times the angular acceleration, which is equivalent to the linear rotation. Now, we now know I, we have a value for that. We don't have a value for these other two things, but we can find torque from the radius times the perpendicular force that's being applied, which we were given. So the torque is 0.35 meters times 55 newtons. So the torque is 19.25 Newton meters. So I can plug that in here. I can plug the moment of inertia in that I just found here, do a little algebra, and I can find alpha. Turns out that alpha equals 62.86 rads per second. The rad's not in here. You have to make that up. This would just be 62.86 per second squared. But what it's referring to is a change in angle, which we're measuring in radians. All right, we still don't know the final angular velocity, which is what we're being asked for. But again, if we go back to your AP equation sheet, find a formula that relates the knowns to the unknowns. Here's one that we used before. Now we can plug this in and find this because we know this value, we know this value, and we know this value. We just go back and look all those up. Here's the initial angular velocity. Here's the angular acceleration. Here's the time that is accelerating. Do the math, and you get 257.9 radians per second. And just to give you context, there's 2 pi radians in a revolution. So if you divided that by 2 pi, you could find out how many times it revolved. Going back to our work equation, 1/2 I omega final squared minus omega initial squared. We now know all these values, and so we could calculate the work being done. And we get around 10,000 joules. Now, it asks us to find the work, which is we just solved, is about 10,000 joules. But it also asks us to find this angular displacement. So if we go back to this formula, delta theta, we just got a value for this, and we have a value for this. So this is 10,000 divided by 19.25, and that gives us 529.15 radians. And again, if you divide that by 2 pi, that tells us that it went around 84 times. So here's your takeaways from this part of the rotational motion unit. Torque is the application of a perpendicular force some distance from a pivot point, which we call the lever arm. If the force is not perpendicular, you can find the perpendicular component by substituting the actual force times the sine of the angle at which it's applied. Work is torque times the change in the angular displacement. And work is also a change in kinetic energy. So in this case, that's a change in rotational kinetic energy, which can be found from the formula 1/2 moment of inertia times the angular velocity squared. Now again, this is a change, so this is going to have a final velocity squared minus an initial velocity squared. And so we could derive that equation and get this 1/2 moment of inertia times omega squared final minus omega squared initial. And again, remember, we could set that equal to this, which we could in turn set equal to this times delta theta. So there's a lot of derivations that you could do. Now, I think it's time to do a few problems.